So welcome to this lecture about surface features. And when we say surface features, we of course mean features that somehow are found on the surface of the objects. And in particular we talk about color and texture. So here's the menu. First we'll start with color. We'll have to say a little bit about how we quantify colors. That brings us to color spaces. Then, by the time we think we have understood it all, we say that it's actually still a bit more complicated and deal with color constancy. And then we will say something about illumination invariant color features, which is a kind of format version of color constancy, if you want. And finally go to the holy grail, which are these bidirectional reflectance distribution functions. More about that later. And that brings us then to the second part about texture. And here we will discuss a few more traditional texture quantification techniques. We will discuss about Fourier features, co-occurrence matrices, and then finally filter banks, so sets of convolution filters, where we will discuss different types. Okay, so I guess that brings us to the first part about color. First of all, I want to introduce this color sensitivity curve called the luminous efficiency function, V of lambda. And as we will soon see, it relates radiometry, the objective measurement of waves like light, and then photometry, the more subjective impression that light gives us. Now, if you look at this curve here, so you have this bell-shaped curve that goes through a maximum, reaching 100% sensitivity. Vertically, you have sensitivity, and horizontally, you have wavelength. So here you have the sensitivity of the human visual system to different wavelengths. And we see it starts as pretty low for the shorter wavelengths that we can see, then rises up, reaches a maximum around 555 nanometers, which is kind of green, to then fall off again as we reach longer wavelengths. So what this curve actually tells us is that if you have a blue light or a red light, monochromatic lights, you would have to put in more energy to give the same visual intensity to a human. In particular, this being referenced 100%, if you go to 50% for instance, if you would have a light, monochromatic light of this wavelength here, 500 something nanometers, reach 50% sensitivity. So in this case you would have to put in the double amount of energy to give the same level of intensity as an impression. Now, such a curve is not easy to generate if you would do it on an individual basis. Actually, people have slightly different curves, only slightly different. In fact, this curve will even shift a bit during your lifetime. So what happened here is that the CIE, the Commission Internationale de l'Éclairage, has defined this average curve for an average adult observer. So it is a curve you could find in the literature specified. Okay. Now, we talked about photometry and radiometry. So photometry is the subjective impression of light that humans get. Whereas radiometry is the objective physical measurement of that light, like the amount of watts. Now, photometry always has been a bit elusive. People have been getting all kinds of definitions of a unit of intensity and so on within photometry itself. That was always pretty shaky. But today, people will go via the very well-defined and fixed definitions of radiometry to then go to photometric units. And let me give an example. So for instance, 1 lumen the unit of brightness, so perceived brightness by a human, is defined via watts. And of course, a watt, unit of power, in physics is very well defined. So now the definition of a lumen, the modern definition of a lumen, is, and it is of course made to match the original definition, but it's much clearer, is that one lumen corresponds to the brightness that you would see for a light source, a monochromatic light source, so a light source of only one wavelength, namely 555 nanometers, so the top of the curve that we in fact saw, the top of this luminance efficiency function. If we put how much power into that monochromatic light source, well, 1 over 683. So if you take a monochromatic light source of 555 nanometers, and with a power of 1 over 683 watt, that is 1 lumen. And you see how many milliwatts that corresponds to. So that is the definition of the lumen as one would use it today. You see it's defined via radiometry. Now, what would then be the intensity of a general light source? Well, suppose we have not a monochromatic source in this case, but we have this general light source with a distribution of power over different wavelengths, C of lambda. So this is power for each wavelength, radiant flux actually. So then you can plug that into this algorithm, into this integral, and calculate the number of lumens, the intensity, the brightness a human perceiver will get from that. And in order to go there, we take the amount of power in a certain wavelength and multiply with this luminous efficiency function, so this sensitivity to that particular wavelength that we saw on the previous slide, and then multiply with K, which is 683 lumens per watt, and that gives us the overall brightness. So we, in fact, decompose the calculation for every single wavelength and then put everything together again in this linear fashion. All right, that as a short note on photometry, we won't say more about it. So why would we want to study color in the first place? Well, of course, it's pleasing to the eye. Humans have color, experience color, we can see color, we take photographs that have color, we watch color television, cinema. So it's so much nicer if we know how to deal with color, if we know how to quantify color. But also as a feature it can be very interesting. If you, for instance, are working in an agricultural application, you have to inspect the quality of fruit. Often the color plays a crucial role. So you want to somehow use color also as a feature to do your analysis and make your classification. Then also you want to generate colors. It's a far more subtle issue than you may think. But if you go, for instance, from one screen to another, you would like to get the same kind of color, and that may require some adaptation. So we have to know how we can quantify colors and transform them when, for instance, exchanging displays. And then finally, it's also, in fact, useful to go through this discussion because it gives us some extra information about how the human visual system works. And in the end, that's the reference of it all, isn't it? Okay. So, light. How do we, well, we see it, but how would we experience it? Well, you could say that there are kind of 3 dimensions, 3 different type of overall features that people will assign to light. And these are the following. We have brightness, we have hue, and we have saturation. And these can be put together into this CIE color space, as it is called. So what you have to imagine this object like is, within this object you have perceivable light, the different colors, intensities and so on that you can see. Outside it not exist as far as a human observer goes. And then you have the different aspects that light can have for us. The first one is intensity. So light can either be completely black, can have a dark environment, or it can even become fully white and everything in between. So this vertical axis that we have here is the axis of brightness. So this overall shape, by the way, is this kind of ellipsoid, American football type of shape. With the vertical axis as said, intensity, and then as you move towards grays here, it opens up, becomes really volumetric. And if you would make a cross section, you would see that over the surface you would have all the different hues, red, green, blue, and so on. And moving away from this axis of grey values, all the greys are here. If you move outside to the rim, you would have higher and higher saturation. So intensity, brightness, hue, and saturation for the 3 dimensions. So in that way you can describe every position in this ellipsoidal kind of color space. Note that indeed it contracts near the bottom and the top there, and what that actually means is that in very dark circumstances, when the brightness is very low, we can hardly see color. And the same happens if we get very bright light. Then it all becomes white to us and we can't tell the difference anymore. As an example, for very dark conditions, suppose you are driving a car at night, there's a car coming towards you. Well, in dark circumstances, you will find it very hard to know the color of that car that comes towards you. In terms of the neurophysiology, as we will see, there are 3 different types of cones in the retina of the human eye. They are responsible for the color perception. And then there are rods. And rods are actually mainly active when the cones are no longer functioning too well. Very dark circumstances, for instance. So at night, we basically have rod vision. And that means we have basically only an intensity level that we can see. We lose color perception. So the rods are not wavelength sensitive, actually. Alright, so now we will see how that looks like, because I can imagine this is a little bit abstract so far. So this is the same space that we had on the previous slide. Okay, so this is the same space, and as I said, on the rim you would find all these different hues, the different colors basically. So you see, go around here, you see different colors. And soon we'll play this movie and you will see these different colors appear as they spin about the vertical axis. Also, as I said, below here it's all black, top there it's all white. And if you would go with the vertical axis through the middle of this color space, you would meet the different gray levels, intense, so yeah, grays of different intensities basically. Alright, so let's move this thing around. So now we'll start to spin about the vertical axis, and you see all these different colors appear on the rim. Now, if you make a cross section, these are different cross sections now, we will look at the middle one. You see very well these 2 other dimensions, hue and saturation. So as you move around, we saw that before, we have the different hues, and if you start from the middle where you have grey, and you move out to the rim, you have higher and higher saturation for that particular hue. Now, as a still, so same story, this is a cross section. Vertically we have luminance, brightness, we have saturation, we have hue as the 3 dimensions. And this is again this middle section that we just saw. You see indeed we have this kind of grey in the center, no real color, it's kind of a neutral reference, you could say. You have different colors if you go around, and you can go from the center to the rim and get higher and higher saturation. So more and more vivid colors. As we will also see later, the colors on the rim, so really fully saturated colors, are actually very rare in nature. And that will help us actually to construct practical color systems. So we just saw that number of 3 appear. So there's something three-dimensional about the human perception of light. Now this has a long history. So in fact the whole study of light starts with Newton. We already saw that Newton understood that if you let fall white light onto a prism, it split up into the different colors, to different wavelengths. Then Young went a step further and was the first to really understand that three-dimensional nature, if you want to represent all the observations humans can experience of light. And what he saw and basically derived a theory for was later given also a neurophysiological, so biological underpinning, when in the eye the 3 cone types were found. So these 3 different kind of cells in our retina, light-sensitive cells, that each sample part of the spectrum that we can see. So there are only 3 of these cone types in the human eye, and in most of mammal eyes as well. And here they are. So vertically, you have relative sensitivity to the different wavelengths, which you find horizontally here. So again, we go from low to high, from bluish, 420 or so nanometers, up to 700 something nanometers, red. This is only a part that's being shown in color. And then you have these 3 curves, H1, H2, and H3. And they represent the sensitivities of the 3 types of cones that we have in our eye. And you see this kind of a bluish cone. It's less sensitive than the others. But it's mainly sensitive to short wavelengths. And then you have this middle cone here, H2, that would mainly be sensitive to that green area. So you say that's kind of a green cone, if you want. And then now you expect, well, you have already blue, you have green, so the next one must be red. RGB, red, green, blue, right? Well, kind of. We see that the 3rd cone is indeed shifted towards the longer wavelength, so it captures more of the red, but it's not really peaking in the red area so much. So it's a bit shifted to lower wavelengths than just red. But anyway, yes, we can call those the red, green, and blue cones, if you like. So 3 different cones, or 3 different cone types, rather, in the retina, with these sensitivities to the different wavelengths. And we call these curves H1, H2, H3. Okay. We will use these 3 curves next. So now we have seen how these 3 different cone types would react to individual wavelengths, these 3 curves we just saw. Those give us a sensitivity to every individual wavelength. And from that we would know their response for a monochromatic source having only a single wavelength. Of course, most light won't be monochromatic. We'll have, as we had before, this distribution C of lambda. So power spread over different wavelengths. And so the question is now, how will the human eye respond to such a general such a general source? And we are interested in three responses. We want to know how each of the three cone types will respond. Okay. And again, we use the same kind of simple linearity assumption as we already used with the luminous efficiency function before. So we have this integral here, a sum, basically, over all the wavelengths. So we take here again the source. It has a certain amount of energy, it's a certain amount of rather power for each wavelength, and we multiply with the sensitivity of the curve that we have selected. Note we have three cones. We have 1, 2, 3, so red, green and blue cones if you want. So once we have selected one of these three, so I has now a value of either 1, 2 or 3. So this is fixed now, a certain h that we take, we multiply the sensitivity for every individual wavelength with how much we have of that wavelength in our source. We sum the entire thing, and that gives us a single response number R. And again, R1, R2, or R3, dependent on the choice of h. So we get three numbers out, three responses. Note that this is kind of inner product that we have. So if you would have this very high dimensional space of all the wavelengths, this is a huge space in sense, very high dimensional. It's like we project the vector c lambda on the three base functions, h1, h2, h3, or just three vectors, reference vectors. So we project c onto three vectors, h1, h2, h3, that gives us three responses. And that's all we know about the light source, the only thing we capture. So it's a very impoverishing perception, you could say. So it's a very impoverished perception. We only get these three numbers out from that complicated interplay of different wavelengths that we have in C lambda. We only get these three numbers, and that's it. That's the way we summarize our perception. So we have only three numbers to go with at the end of the story. And that has implications. It also means that if I would choose two functions, c of lambda, let's say c1 of lambda, c2 of lambda, and you will both yield me the same three numbers here on the left-hand side, the three responses to of my cones are the same, then I can't tell the difference between the two light sources. So I may have two light sources with very different spectral compositions, and yet I can't tell the difference if the three responses, R1, R2, R3, are the same. If my three cone types react in the same way. We see the same color, so to speak. So that's kind of sobering. Remember that in the past we said if you have a certain wavelength, if you have in fact a monochromatic source with only a certain wavelength in it, that implies that you see a certain color. That is what we saw, I think, 2 lectures back. Now here you see why you can't reverse that. It may very well be that you see a certain color, but that does not let you conclude that therefore there can only be this one wavelength from that table that we then saw in the light source. You can say pretty little about the light source actually. There could be a monochromatic light source, could be light sources with multiple wavelengths in them, and also multiple C lambdas with multiple wavelengths in them are still possible. So, yeah, the eye lets itself being fooled in that sense. And of course we make use of that when looking at television screens and so on. That's exploiting this weakness of our visual system. Also note that we assume, here and elsewhere, that intensity and chrominance, so the actual brightness information and the color that we see are kind of orthogonal to each other. Meaning, in this case, for instance, if I would add the power for different wavelengths by 10% for all the wavelengths in C, our assumption is we see the same color, it's just brighter. Now, this linearity assumption underlying this integral is not exactly true, but to a very high degree. And its orthogonality is also not exactly true, but again, to a very high degree. So we'll just go with these simplifying assumptions. Then a word about so-called color blindness. I'm going back to the human visual system here. So about 10% of our population have abnormal color vision. And color blindness is a little bit of a misnomer in a certain sense. So what happens in most of colorblind people is that they have one cone that is a bit different from the normal cones. So in fact, they make also 3 projections. They have 3 different cone types, make 3 of these projections, but one of these axes is a bit off. So they make a projection on a different vector for one of these h's here, and therefore get different numbers R than normal observers would have. And then of course you can play all kinds of nasty games and pester these people by showing this kind of stimuli where a normal observer with the normal types of cones that the majority has will see a difference between background and foreground, but the colorblind person may not be able to distinguish. But note that we can also play the opposite game. You could also, in fact, show to a normal observer plates like these, where the normal observer would not see a difference between foreground and background, but where the colorblind person can. It's just a matter of making sure that you take patterns where background and foreground yield the same R's for a normal observer and different R's, the third R, the third cone, the deviating cone, should give a different response for the colorblind person. Now, I have to say that there are rare cases where people even have only 2 kinds of cones, or in very exceptional cases, even only a single kind of cone. Of course, that then really strongly starts to impoverish the color perception. If you have only one kind of cone left, you basically only see intensity. Okay, further. Mammals typically have 3 different types of cones, but for instance, many birds have 4. So you can imagine the entire theory I'll start to discuss here about color perception would be quite different for a bird. You would need a different lecture on that one. For instance, birds often also see ultraviolet. And then last but not least, so far I've been telling you the story like, when it comes to the observation of light, it all goes down to having these 3 R values. Okay, that's what it all boils down to. You have the 3 R's, the 3 responses of the 3 curve types. That's it. That's the way you see light. Now, this is not entirely true. Again, there's an additional complication here from context. So a scene typically has multiple colors, multiple lights coming back towards our eye, and that context, that environment will play a role as well, as we'll also see later on. So it's not all in the R's, there is something more.